My name is Arpan, and I'm a PhD candidate in Florida International University. Today, I will be presenting an article with title STRCacheML, a machine learning assisted content caching policy for streaming services. So based on the title, we can understand this is about the caching policy. So let's understand what is the cache memory. So the cache memory is a limited memory, like a small memory, which keep the data which are frequently accessed. It is used for fast retrieval of data. It can be used in our computer, or it can be used on server, and so on. So here, let's understand a little bit about cache functioning with a rough diagram. So this is the main memory. Let's consider this as a size 5. And here is a cache memory with size 3. And there are users that access the videos. And let's say first user access video 1. And we look in the cache memory. And if we see there is space in cache memory, we put the video accessed into the cache memory. And on the second step, let's say the video 2 was accessed. And also, again, we look for the space, and if there is a space, we store here. And on the step 3, the video 3 was accessed, and so on. So on this level, when we request the video 2 again, when someone requests the video 2 and it is in the cache memory, we provide from the cache memory. But let's say if the video 5 was accessed and the cache memory is already full, and this time we want to make first space in order to store it. And there it comes about cache replacement, and we want to replace a data that is less important rather than important. So we have some mechanism in order to replace the cache objects from the memory. These are called cache replacement. And after that, we insert the value, and we keep cache hit and cache misses. And here are some established cache replacement policies, and they are LRU, MRU, LFU, and LRFU. The least recently used caching policy here, like for example, we have a cache memory as we talked before, and when the cache memory is full, when it is time for the eviction, this policy evict the one which is evict the cache object which has been in the cache for longest period of time. And the second one, most recently used, this when it is time for the eviction, when we need to make a space, it will evict the one which is recently accessed. For example, the idea is that the video that is recently watched may not be watched again right on the next access, but the one which has been in the cache memory for the oldest time may be accessed in the next time. So we keep the oldest data and evict the new one. And the LFU, least frequently used, this cache replacement policy will actually keep the number of time the cache objects were accessed rather than the time period. So for the eviction, this will select the one which has been accessed for least amount of time. And another one is LRFU, and this is kind of utilize both LRU and LFU idea. And the one when we want to evict a data from the memory, it will select the one which is least frequently and least recently has been used. And the work on this in this paper was to build a recommendation engine for video streaming services. And to do that, we wanted to use the features which are available within the data. Let's move to the another slide. Here, for example, we already see that we want to do cache replacement. And to do that, this replacement policy either use the time of access or number of the access. The question would be, can we go beyond that? Yes, we can do that. We can understand the underlying features of the cache accesses. We can use machine learning algorithms in order to train into the data set that we have to understand the data accesses. And then based on the training, once we have the understanding of the underlying patterns, we can use the machine learning in order to make cache eviction and to have better cache replacement policies. In the paper we propose STRCacheML, which utilizes the machine learning algorithm. Here we divide the idea into 4 sections: section A, section B, section C, and section D. For the section A, since we wanted to do some recommendation suggestion, so we used a dataset from the IMDb website. And since we collected data from the official website, the data was raw, and we had to do some pre-processing to have the defined data set. And for the section B, since we are using a simulative environment, we had to do simulation, and we determine our cache objects, and we also simulate the cache inquiries and cache memories. After that, so we want to use the machine learning. In order to that, we have to have a data set that can provide some labels, that can give some decisions. So to have that kind of data set, we use IMDb data set, and we use simulation in order to have the data set and the labels. For that, after that, in the section C, we selected some lightweight machine learning algorithms. We trained the machine learning algorithms in the given constructed data set, and we use the metrics like in the metrics that is generally used in machine learning, like training and testing accuracy. Based on the accuracies, we selected the one with the highest accuracy in both train and test, and that was used in the STRCacheML. So now during the cache management, so STRCacheML will use the trained machine learning algorithm and will utilize the given feature while making the cache eviction decision. So to continue our talk about the dataset data preprocessing, so actually we access the data from the IMDb dataset, which is given here in the link, and we actually it was accessed 1 year from today, almost 1 year from today. For the pre-processing steps, there were some missing values in the columns. We had to do some pre-processing using scikit-learn. For example, we just used average of the values in order to insert in the missing columns, or we simply remove the rows in order to have a refined data set. After that, so we wanted to make the utilization of given features within the dataset to have some cache accesses, because cache accesses are in general are impacted by some features, and we wanted to use the features for example, genre, ratings, and so on. And also we wanted to do some temporal feature that the given cache will be changed with the given time or a given number of days. Here on the first process, we had to do simulation. Actually, we did a good a way to feature engineer. For example, so we know that the given any dataset forms a distribution, but we do not know that what distribution they form. In order to have that kind of distribution within the given cache accesses, we use the number of votes to do the probability distribution. For example, if a given movie has more number of votes compared to another movie which has less number of votes, then that movie will be more likely to be accessed in the another inquiry. So also we determine the cache sizes, and upon close investigation, for example, the final idea is that we want to understand which given data, if we access, will lead to cache hit. Cache hit means if the data that was accessed by the user is in the cache memory. So that was the final goal. So we make that kind of goal as our final outcome and set up the classification so that we can train classification machine learning algorithms. And for the data was feature vectors. that represent the inquiry. For example, one hot encoding of the names, genre, when the last time it was accessed, and these were the data. And also for the labels, it does that inquiry, let's say we did our inquiry on the given data, does that inquiry will lead to cache hit that the data is in the cache memory or it is not? That was the label. So right now we can understand that the platform we are thinking about is supervised, that we have labels and we select different machine learning algorithms like random forest, gradient boosting machine, k-nearest neighbor, multi-layer perceptron. We split the data into 80-20 ratio. This is general way of splitting data in the machine learning processes. And we did some hyperparameter tuning. Basically, morely, the KNN and MLP were performing better than others. So we mainly focus on KNN and MLP. So, and for KNN, we try to do experiment with different number of neighbors, K neighbors, and we found out that the 5K nearest neighbor was giving us good accuracy and also a good time in a less time complex. And for MLP, we did experiment with different hidden layers and also with the different number of nodes. And in general, we found that two number of hidden layers with 128 and 64 number of nodes were giving us good accuracies, also within the certain time complex. And for the evaluation metrics, we simply, as I already mentioned, we used training and testing accuracies, and based on this accuracy, we can understand how good machine learning algorithm was performing in the constructed dataset. And for our final selection, we selected the one which had both good accuracy in train and test set. Here is the visualization of the model training and testing on all machine learning algorithms, this subset of the machine learning algorithms. Uh, the blue bar shows the training accuracy, whereas the green bar shows the testing accuracy. If we see here, MLP was performing good on both train and test set, but the random forest was also performing good in training set, but it failed to even get like 80% of accuracy, and we determined that it was overfitting. And so we selected MLP as our final machine learning to be used to understand the data and to do the final eviction. Now here come the STRCacheML, and as I already mentioned that MLP was the final machine learning algorithm, and we simulate the cache behavior as using the probability distribution on the number of words. And now let's say we have a cache memory, and that the cache memory after a certain period of accesses was full, and rather than using just time of accesses, we use those features that were constructed and the MLP to get the least likelihood of being requested in the next access. For example, there could be data 1, data 2, data 3. Now we want to evict one of the data. Then STRCacheML will calculate the likelihood score that will be from 0 to 1 for 1, 2, 3, and the one which will have the least likelihood score will be evicted to make the space to store a new data. And also after that, we have that mechanism in STRCacheML to track the cache hits and cache misses. Here's the experimental setup. So we used Python 3.1012 version, and we trained this in T4 GPU with 15 GB of GPU RAM. And we experimented in two different simulations. Simulation 1 was contained the cache inquiries of 10,000, and the cache size was 25. In the simulation 2, we doubled the size of inquiries and the cache size, and the performance metrics were cache hits and cache hit rates. As in, cache hit rates was able to give us more information on what number of cache accesses lead to the cache hits, and we compare our machine learning, our content caching policy with LRU, LFU, and LRFU. Okay, here is the actually experiments and results in the table I. As we see in the simulation one, STRCacheML got 1078 and on the raw caches, and it got 10.78 in hit rate. And also in simulation 2, it got 3770 and 18.85 of the hit rate. We can see that STRCacheML was performing better than all of these established cache replacement policies. One thing it was interesting to see was like LRU, LFU, and LRFU. In the literature, LFU is better than LRU, and LRFU is better than LFU and LRU, and which is also seen in our experiment that it is performing better than all of these models, and also but it was not performing better than ours. So ours was the one which overcome all of these cache replacement policies. Okay, let's move to the visual representation of cache hit rates. Here is the graph that was used, that was drawn on each cache inquiries. And also the red, actually the red plot here is the red line is the one that was obtained by STRCacheML. And we can see that on each cache inquiries and cache number, the cache hit rate was better as compared to all of these models. And on the simulation 2, here's the representation of cache hit rates. And again, the red graph line represents the cache hit rate obtained from STRCacheML. We can see that it is still performing better as compared to all of these models. And based on each query numbers, it is performing better. So here, so in the conclusion, I don't have the conclusion here, but the conclusion was that we can use the simulative environment. Using that, we can also estimate the probability distribution of the given data using number of votes. Based on that, we can use the feature construction, and we were able to train the machine learning, and we were able to get better accuracies. So that was our contribution. And for the future work, we can actually, as we see that we use the machine learning to train, this idea can be explored to different platforms. So our future work will explore more data set, and also if we use different platform, the parameter, the feature used in this platform may not be useful. So we have to be careful with that, and we want to explore some more feature engineering in future. And if you see right now, the idea was used on offline mode, and we did not consider about user privacy during understanding the underlying features. So in future, if we use this into the different data set or in the different setup, we will also thinking about considering privacy and security. And we want to investigate advanced deep learning methods like RNN and transformer. But the thing is that we need to consider about time complexity. Our idea could be simple, but we don't want to make it very complex using very complex deep learning algorithms. But we are thinking to investigate that. And also in cache replacement policies, like in cache management thing, there could be data that could be influenced with short-term dependency. For example, in YouTube or TikTok, the videos could get trained for short period of time, and some will get trained after long period of time. We want to use this kind of platform, and we want to use our STRCacheML and make a hybrid model so that we can have that kind of understanding and get a better results. That will conclude my presentation. Thank you for your time. Feel free.